for the experimental determination of the bond energy of paraffin, which is a type of wax. So in class, we've been using a table of average bond energies to calculate the bond energy for chemical reactions. Here, we're going to do that same thing, but experimentally. It's a different technique that as we break the chemical bonds in the candle, that heat energy will be released to a can of water. And so we will be able to calculate the heat gained by the water using this mathematical equation: the mass of the water, the specific heat of the water, the change in temperature of the water. So we start off with some percent by mass values for carbon and hydrogen. And it says determine the mole ratio. So if I'm not given any other information, I just know that the compound is 85% carbon, then I can assume that that percent is grams in a 100 gram sample. If I knew the size of the sample, I could multiply that percent by that mass and determine the actual number of moles of carbon. But here we'll just make this assumption. So I'm assuming each number is grams, and I'm going through the process of changing that number to moles. Remember, you can cancel grams and determine moles using the molar mass. We do not need to double the molar mass of hydrogen because we're not talking about H2, a molecule alone. We're talking about H within the paraffin molecule. So if we go ahead and do that, we get 7 moles of carbon, 14 moles of hydrogen, which is approximately a 1-to-2 ratio. I'd love to skip this item if possible because it's a little wacky and I haven't figured out what's wrong with it. But essentially, it was supposed to be a clever way for us to come up with this compound. The compound was given to us above, so we're just using this compound going forward. Now, can we write a balanced equation for the combustion of that compound? It reacts with oxygen, makes carbon dioxide, and water. That is the definition of a combustion reaction. And then we balanced it together as a class, so you can see the coefficients written right here. The next step then was to do a little bit of stoichiometry. So with that balanced equation from above, it says we have 27 grams of a candle being burned completely. So all 27 grams are reacting. How many grams of carbon dioxide will be formed? So I'm setting up a BCA table. Of course, you can use a railroad track or another method that you're aware of. And I'm just filling in the 27 grams. And the thing that I don't know, which is how many grams of carbon dioxide. I just like to annotate with a little question mark there to keep me motivated. And before, I need to plug in values that are in moles. So I have to turn that 27 grams into moles. And here's the molar mass for the paraffin wax. Okay, and so when I did that math, I got 0.096 moles of this. I'm assuming there's excess oxygen, and of course there are no products. So now I have to fill in the change line. So if all the moles of the wax change in the chemical reaction, then remember I divide by the coefficient above, multiply by the coefficient I want to fill in, and I have my new value for moles. I wasn't really asked about oxygen, but let's go ahead and do that exact same math for carbon dioxide, and that's the value I was asked about. Now, my last step, since I was asked for grams, I must change the mole value into grams. So 1.9 moles, and the molar mass of carbon dioxide, I get grams. All right, so by burning 27 grams of a candle, I will produce this much carbon dioxide. All of that was hopefully some review for you. The new part is number 6. It's a sample of what the lab calculations will actually be. So if this makes sense, it'll make the last part of the lab much easier. Let's take a look. Liquid water has a specific heat. Specific heat is a value that you should have learned about sophomore year. Its symbol is a lowercase c. It's the amount of joules of energy required to change the temperature of 1 gram of water by 1 degree Celsius. So how much energy does it take to heat water and change its temperature? And that number is a constant. It's 4.18. You could always look it up. So what's the question asking then? How much energy is required if 75 grams, that's the mass, of water initially at this temperature heated to this temperature? So they're giving us a delta T. And how much energy? The symbol for energy is Q. We have to now look for a relationship that relates the specific heat of a substance with how much energy it produces, the mass of that substance, and the change in temperature of that substance. That relationship was given to us above. Heat gained by the water is the mass times the specific heat times the change in temperature. Q equals mc delta T. Our given mass, our specific heat, and our change in temperature. If the units are matching, then we should be fine to go forward with this calculation. Let's check the units. We have grams here and grams in the denominator. That unit will cancel. We have degrees Celsius here in the denominator and degrees Celsius that's being subtracted from itself. So those units will also cancel. The unit we'll be left with is joules, and that is a unit for energy, so that makes sense. So let's do the calculations. 32 minus 11, and then I simply multiply the three values, and I get 6,000 joules of energy gained by the water. By the way, that would be 6.5 kilojoules, since our homework was kilojoules per mole. So the lab may ask you to take the kilojoule value and divide it by the moles of the candle burned. So let's talk a little bit about the procedure. There are some advantages and some disadvantages to this methodology. One, we wanted to demonstrate that science is attainable to everyone. So here's our apparatus for capturing the heat energy. It's two nested cans. The bottom of the first one has holes in it to allow oxygen in. The candle burning inside can continue its combustion. And then the secondary can has water inside, and that's the water we're using to capture the heat energy. I have them nested together in this system, and I'm going to use the ring stand just to kind of lower. I want to find a height where I don't snuff the candle out, but yet I can capture the majority of the heat energy. So we're taking the temperature of this water, so that will give us our delta T value. You don't have to have the most expensive, high-tech equipment. You could just make an apparatus to answer a small question. And that's something we think is pretty exciting. Take chemistry into your real world. However, one of the disadvantages of our system is that it wasn't well insulated. It had a lot of holes, and so there was a lot of room for heat to be conducted into the surrounding air and lost by the system. So I think our calculated value will be quite a bit less for the experiment than using the table of bond energies.